Hello everyone, I'm Sonny Collado and once again I am here telling you some topics. Today we got gases. What are gases? Well, the gases are particles that moves fast in a container. But more specifically are just as we talk in the first topic. In the first topic we talk about how the matter can be divided in three things: the solid, liquid, and gas. The gas, we know that their molecules or atoms are more wide separate than the other ones, like are the liquid and uh, solid. The gas, as they are so separated, makes this form. So thanks to this form is because we know it is fast. Its molecules are fast and they move a lot. So it is also known because it makes a straight line. But if it grows with a wall, for example, it can take the shape of that wall, for example. And not only that, it can bounce not only with the wall, can bounce also with its same molecules. Okay. In this topic, we are not going to talk about only the gases. We are going to talk about also the deepest topics of it, like are the pressure gas. The pressure gas is going to be the force exerted by the molecules inside a container. Um, and this is caused because of the fast and aggressive movements that the molecules and particles are having inside the container. So it's that makes a compression on the container, and when you open it, that can, pah, you know. So that's what happened with it. The gas pressure is not going to be a simple thing. Is going to be separated in three several parts. So the first part is that the gas pressure will depend on how much gas particles there are in a container. Will be that's the first one. The second one will depend on how much volume has the container. And third one, it will depend on how fast the particles are gonna travel into the container. Depending on how fast, more pressure. So yes. Now we go with my partners and see what we got.
Hello everyone, my name is Valeria Hilsa. I'm going to talk about Boyle's Law in this chapter 6, which is one of the basic Gauss law in chemistry. Boyle's Law explains the relationship between the pressure and the volume of a gas. It states that when a temperature and the amount of gas is the same, pressure and volume have an inverse relationship. This means if the pressure increases, the volume decrease. On the other hand, if the pressure decreases and the volume increases, the relationship is expressed by the equation of P1 B1 equals to P2 B2. The way to understand Boyle's law is by thinking about a syringe. When you push the plunger, the air inside has less space, so its volume decreases, but the gas is compressed into a small space. The pressure increases. When you pull the plunger back, the volume increase and the pressure decrease. Another real life sample mentioned in our chapter is scuba diving. As the divers go deep into the water, the pressure increases because of the weight of the water above them. This causes the air in their lungs and the equipment to occupy a smaller volume. When the divers rise back to the surface, the pressure decreases and the air expands. This is why divers are taught to breathe out as they ascend to avoid injuries. In a conclusion, Boyle's law helps us to understand how gases behave under different pressures. It is important to in many everyday situations, such as syringes, bicycle pumps, and scuba diving. Understanding this law also helps scientists and healthcare professionals work safely with gases in many different files.
Hello, my name is Nathaniel Masintabon, and I will be talking about Chapter 6's Charles Law. Now, this applies to gases in which the volume of a fixed amount of gas increases with the increasing temperature, and changes are, in a sense, parallel to one another. The next volume, there's an initial volume and a final volume, initial temperature, final temperature. Now, this is all measured in Kelvin, and thus everything in this must be recorded as Kelvin in terms of temperature, in terms of how temperature affects volume. Now, here you see a graph of how temperature and volume operate in terms of uh, like in terms of their proportion to one another. As temperature increases, volume increases, and volume can, well, temperature can never be exactly zero, as you see here. In terms of molecular view, here's a balloon. Hotter water, the air molecules bounce around and thus increase the volume, while in ice water, the gas molecules remain inert, in a sense, and more compact. So when temperature increases, the collisions of molecules within the container is greater, increasing volume.
Hi, Dr. Sharma. This is Carlene doing my video review for Chapter 6. For Chapter 6, when it comes to things that I found challenging, I actually didn't find this chapter nearly as challenging as the rest of the ones in earlier chapters. And hate to say it, but probably because this one didn't require as much critical thinking. It was pretty straightforward, you know? Even the math was even worlds easier. So it was easy to kind of digest when it came to the concepts or whatnot. Not that the other ones were crazy difficult. The math was like a little more work, but it wasn't too bad. But this one was just really easy for me. I decided to do my chapter review on kinetic molecular theory. Oh, excuse me. It's a theory that I wrote a couple notes down. It's a theory that explains how the molecular nature of gas gives rise to their microscopic properties. So, gas laws enable us to predict the macroscopic behavior of gas, but they don't explain why they behave that way. So kinetic molecular theory was put forth by a number of physics to explain how molecular nature of gases give rise to their macroscopic properties. So there are 4 assumptions when it comes to kinetic molecular theory. One is a gas is composed of particles that are separated by relatively large distances. The volume occupied by individual molecules is negligible. 2 is gas molecules are consistently in random motion, moving in straight paths, colliding with the walls of their container and with one another in perfectly elastic collisions. Energy is transferred but not lost in those collisions. 3 is 3 molecules do not exert attractive or repulsive. I said 3 molecules, but it is number 3. Gas molecules do not exert attractive or repulsive forces on one another. For number 4, it's the average kinetic energy of gas molecules in a sample is proportional to their absolute temperature. So with that being said, it's important to understand that gases are compressible because molecules in gas phases are separated by large distances, which is assumption number 1. They can be moved closer together by decreasing the volume occupied by a sample of gas. And you can do that by applying weight onto whatever container that they are in, or force, you could say. and it creates more pressure in the container as a result because they have less volume. So with that being said, Boyle's law is relative in this case, with the pressure exerted by gas is a result of collisions of gas molecules with the walls of their container. The magnitude of the pressure depends on both the force of collision and the speed of molecules when they collide. So that's what I just went on to say. Decreasing the volume occupied by a sample of gas increases the frequency of those collisions, thus increasing the pressure. Charles' law is relevant here because heating a sample gas increases its average kinetic energy. Assumption number 4. Because the masses of the molecules do not change, an increase of average kinetic energy must be accompanied by an increase in the mean square speed of the molecules. In other words, heating a sample of gas makes the gas molecules move faster. Fast-moving molecules collide more frequently and at greater speeds at impact, thus increasing the pressure. And I'll insert an image there too so you guys can see. And then Avogadro's law is relevant to kinetic theory because let's see here. Because the magnitude of pressure exerted by a sample of gas depends on the frequency of collisions with the container wall, the presence of more molecules would cause an increase of pressure. Again, a container will expand if it can. Expansion of the container will decrease the frequency of collisions until the pressure inside and outside the container are once again equal. And that's where Dalton's law of partial pressures comes into things. Gas molecules do not attract or repel one another, which is assumption 3. So the pressures exerted by one gas is unaffected by the presence of another gas. Consequently, the total pressure exerted by a mixture of gas is simply the sum of partial pressures of the individual components in the mixture. And through that, you can probably, it says here that you can find molecular speed, but I don't think we went into that. But I'll insert a couple images so you guys can see that. Thank you.
In Chapter 6, I learned about reactions involving gases and how to use gas volumes in stoichiometry. Instead of only working with moles, you can also use the volume of a gas at a specific temperature and pressure. To solve these problems, you can use the ideal gas law to convert between gas volume and moles. When a gas is at standard temperature and pressure, you can use the relationship that 1 mole of gas equals 22.4 liters. I also learned that sometimes the pressure used in calculations can be the partial pressure of a gas. The biggest challenge in this topic for me was learning when exactly to convert gas volumes into moles. At first I wanted to use gas volumes to convert to the gas volumes directly, but this led to mistakes. To overcome this challenge, I just made a simple checklist of the exact steps of converting moles to volume and volume to moles. And, this helped me a lot more to understand.